Hello everyone, in this video we are going to look into the design of ALU, arithmetic logic unit. We are going to design a basic arithmetic logic unit in Verilog and going to see how it works and how an ALU performs in a CPU. So first, the ALU is nothing but an arithmetic logic performer. So it gets an operation code and then two operands to perform some operations. Like for example, if you want to add some variables a plus b, you'll be giving the a and b into the ALU, and you'll be sending an opcode to telling it the ALU to add the two variables. Okay, the opcode is nothing but a random code you give to the ALU to tell the ALU what operation should it perform. So you'll be getting to understand it when we are going into the code. So first, this is the basic of ALU, and it will be resulting as a output. So let's get into the code. Here we are. This is our ALU code. We are specifying the module name. We are giving the input ports and output ports like A, B, and we are providing an opcode of length 0 to 3. That is the 4-bit opcode. And we are going for an enable signal to mention the ALU that it should turn on. Like enable signal wakes up the ALU to perform an operation. Next, the output is the ALU out, where we will be getting our output like a sum or a difference. And the output register, here we are mentioning 5 flags to determine the carry, negative, 0, and overflow flags. So these flags are nothing but the output flags that mentions whether the output is a negative or whether the output has a carry or it overflows the given size or it has a 0 output. So these flags will be useful when we are performing an operation in a very large scale CPU or a GPU application. So basic ALUs have these flags to perform an operation. So we will be taking a look into that when we are going into performance. So next we are declaring a wedge variable temp, and we are having the parameters to mention the opcode in a variable. So we are having add sub, increment, decrement, and or zor not, and this is a single left shift and single right shift, and this is an arithmetic right shift. So these are the opcodes we are gonna feed into our ALU. These variables will be used by these operators. So first, we are declaring an always block to make it as a behavioral model. Always, whenever any variable changes, it will be acting. So it's a combinational block, and we are setting the variables to 0 at the beginning of the clock cycle, and we are going to check whether the enable signal is high or not. So if the enable is high, we will be beginning this block and getting into the case statement of opcode. When the opcode is changing, these variables will be acting into the ALU. In the case statement, we are having our opcode variables with their particular blocks. In the add section, we are just simply adding the operands and putting it into a temporary register to perform the operation. Next, we are putting the temporary register into the ALU out. This is just the output of the ALU. And we will be doing the same thing in all the sections, like subtraction. We will be performing the subtraction and we will be getting it into the ALU out. And in the increment, we will be incrementing the variable, and decrement, we will be decrementing the variable. And in the XOR and OR gate operations, we will be performing the gate operations with the symbols. And in the left shift and right shift, we will be using the operands. And we will, in the arithmetic right shift, we will be doing the arithmetic right shift formula. It is nothing but we will be just keeping the last variable in its position, and we will be shifting the variables shifting the bit 1 by 1, 3 to 1. So these are the operations we'll be performing. The different thing you will be noticing here is nothing but the carry, overflow, these flags. We will be calculating these flags according to the output of the current operation, and we will be putting it into the register. Here we are. If the variable has a carry value, like if we add two operands and we have a carry, then it will be putting it into the carry variable. And if the output is more than the number of bit mentioned, like it is crossing the size of the memory, we will be putting it in the overflow variable. Similarly, we will be putting the carry into the carry variable and overflow in the overflow variable in the subtraction too. In the increment, we will be calculating the carry, and similarly for the decrement. And in the gate operation, we won't be needing the flags. Similarly for the shift operations, we will be calculating the carry. So these carry and overflow has some formula you can perform with. This overflow can be calculated by checking whether the first, like the MSB variable of the both operands are equal or not. If those MSB variables are equal, and also with the output of the MSB variable is not equal to the first variable, then in the add operations, we will be giving the overflow flag as high. If it is in the opposite case, like in the vice versa case, we will be raising the overflow of subtraction. This is what happens in an ALU. So this is a simple code. We will be performing an operation based on the opcode given in the data. So this opcode is nothing but the instruction that is came with the instruction set. For example, the instruction set will be like this, and the first part from 31 to 6, the opcode will be basically 6-bit, but we are using a 4-bit ALU and we are providing a 4-bit opcode. But in the real scenario, like a MIPS32 processors, you will be having an opcode of 6-bit. So you'll be having a lot of operations going on into the ALU. So the opcode will be in the particular space in the instruction set, and that will be decoded and used in an ALU, like a feed into the ALU. So we will be putting that opcode into the ALU, and ALU will be performing the operation based on the opcode it receives. So I actually used a flag register to store these flags, so I can just give them output in a proper way for you guys. So I can just display it in a proper way. But in real scenarios, these flags will be going into a memory. I'm just using a simple register variable to store these registers. Okay, let's see the output. I'm just running it. So the simulation result will be like this. Yeah. We are having the clock. The clock will be useless here because it's a combinational block. I'm just giving it for the time scale to perform properly. So if the enable signal is high, we will be performing an operation. Whichever data comes in A and B registers, we are having 3 and 4 in an A and B, and we will be performing an operation based on the opcode. We are having an opcode of 0, so we will be performing add operation. So the ALU out will be A plus B, 3 plus 4 equal to 7. So this is the output, and the carry flags will be like this. When we are adding these operands like 5 and 3, we will be having the output as what? We will be subtracting it. We will be having as 2. So the carry will be high at the time when we are giving the negative MSB variable. So you can just go through it. So you can just get what the carry variables and negative variables are doing in here. So the code is in the Github. So you can just pull the code into your own VS Code or Vivado. So you can run the code and test yourself. You can find the Github link in the description. So go on. For more useful videos, subscribe to this channel. So a lot of designs are coming through, and these are my first videos. So keep supporting. Thank you.